Hey guys, what's up? This video is part of our guide for our CXC physics syllabus, and today we'll be focusing on work, energy and power.
First, we'll start with work and energy. Now, you may use these words in your typical day, and so you might have some understanding of their meanings. But what do you think they mean in terms of physics? Well, that's why we have done this video.
Alright, in physics, work is defined as energy transferred from one force, and energy is defined as the ability to do work. Both work and energy use the unit joules.
To figure out the work something has done is more or less straightforward. The work done is equal to the force of an object times the distance of the object is moved to the force's direction. For example, if we use a force of 10 newtons to lift a bag and we lift up by 2 meters, how much work have we done? Well, if the force is 10 newtons and the distance is 2 meters, we can just plug these values in our equation, and when we work out this, we will get 10 newtons meter. 1 newton meter is equivalent to 1 joule, so we have done 20 joules of work.
Here's another example of using the equation for work, but now we'll use this equation to find something else. Let's say 5 newtons to push a block, and we end doing 20 joules of work. How far did we push the block? To figure this out, we'll use the same equation, work done equals force multiplied by displacement. And when we plug everything in, we get 20 joules equals 5 newtons multiplied by displacement. To find the displacement, we just divide both sides by 5 newtons, so that cancels out on the right, and we are left with displacement equals 20 joules divided by 5 newtons, which is equal to 4 meters. If you're confused how joules divided by newtons equals meters, remember that 1 joule is the same as 1 newton meter. Alright, this is basically how you find work, and you can use it to find other stuff.
As you just saw, finding work is relatively easy, right? But in order to figure out energy, you first got to find out what type of energy it is.
There are various different types of energy, but today we will be focusing on 2 most often used forms. The first one is called kinetic energy. This energy, due to motion, and all moving objects will have this type of energy. The second type we'll be looking at today is called gravitational potential energy. I know the name sounds really long and confusing, but it's actually not that bad. This kind of energy is the energy an object has based on its position in the gravitational field. So to break that down, if I hold up a stone, that stone will drop because of the gravity, right? Well, the energy that the stone has because of this is its gravitational potential energy. And you'll see in a moment how it is related to kinetic energy when solving problems.
Alright, with the definitions out of the way. Now we have to move on to a very important concept that involves all types of energy. This concept is conservation of energy.
To do work, you have to use energy, right? But just like money, the energy doesn't disappear when you use it. Instead, it goes somewhere else. People often say using up energy, but energy is never actually used up. It just changes into different forms.
Whenever energy changes into different forms, scientists say it is transformed. As you can see in the diagram, when you throw something like a stone, energy is being changed into different forms. Before you can even throw it, the chemical energy in your body gives the muscles the power to move. Now that the muscles and the neck and the rock are moving, it is transformed into kinetic energy. When the rock is at its highest point in the air, its potential energy is at its max. Then this becomes kinetic energy again, and the stone falls to the ground. Once the stone hits the ground, it is transformed into thermal energy.
In that example, energy transformations look kind of like a simple chain. In reality, though energy is lost from the system at each stage, for example, muscles convert less than 20% of the stored chemical energy into kinetic energy. Instead, most of it is wasted as thermal energy, which is the same reason why you sweat so much during exercise. Now, although some of the energy gets wasted, the total amount of energy stays the same. And now, it's really important you guys remember that.
Alright, now we'll focus on the equations to find these two types of energy. The equation for gravitational potential energy is gravitational potential energy equals mass multiplied by force due to gravity multiplied by height. This can be written using abbreviations like this: GPE equals mgh. The equation for kinetic energy is kinetic energy equals half multiplied by mass multiplied by velocity squared. This can be written using the abbreviations KE equals half mv squared. Now that you guys know these equations, we can finally move on to solving some problems.
Let's say we have a stone of 5 kilograms that is 10 meters up in the air. What is the stone's gravitational potential energy, or GPE for short? Well, to find this, we can simply plug this into the equation we just wrote. So GPE, which we're trying to figure out, is equal to mass 5 kilograms times the force of gravity, which is always 10 newtons divided by kilograms on Earth, times height, 10 meters. So we have GPE equals 10 kilograms multiplied by 10 newtons divided by kilograms multiplied by 10 meters. The kilograms unit cancels out, and we're left with 5 times 10 newtons multiplied by 10 meters, which is 500 Newton meters. As we explained earlier in the video, Newton meters is the same as joules. So 500 Newton meters is 500 joules. So the stone's GPE is equal to 500 joules.
Now let's try a kinetic energy problem. We have a textbook of 10 kilograms being dropped at a velocity of 2 meters per second. What is the textbook's kinetic energy? Same as before, we just plug everything into our handy-dandy equation. Kinetic energy of Ke is equal to mass. 10 kilograms times velocity squared will be 2 meters per second squared. 2 meters per second squared is 4 meters squared per second squared. So now we have 10 kilograms times 4 meters squared per second squared, which is 40 kilograms meters squared per second squared. Now I know these units look very confusing, but just remember that joules is the same as meters, meters. And Newton is force, which is mass times acceleration. So its units are kgm per second squared. This all means the base units for joule are kgm squared per second squared, which is exactly what we have up here. So the textbook was 40 joules of kinetic energy.
For our last example in this, we'll solve a problem that uses everything we just learned about energy. Alright, so we have a cricket ball of 4 kilograms being dropped at 4 meters from the ground. What is the stone's kinetic energy halfway to the ground? Now I know some of you are already freaking out because this looks like a GPE problem, and suddenly I'm asking for kinetic energy. But just remember how energy is transformed. This means that the GPE of the stone doesn't just stay as it is, but most of the time it is transformed into kinetic energy. With this we can solve the problem.
4 multiplied by 10 newtons multiplied by 2 meters, which is equal to 8 meters multiplied by 10 newtons, which is 80 newton meters or 80 joules. So our GPE is 80 joules.
To solve this problem, we just have to remember that the ball's GPE, which is lost, is transformed into kinetic energy. So halfway at the bottom, 80 joules of energy are lost because of our distance is now 2 meters. But like you should know, energy doesn't disappear, it is transformed. So this is 80 joules of GPE lost by the stone is transformed into kinetic energy, meaning that halfway at the bottom, its kinetic energy equals 80 joules. And that's how you solve the problem like this.
Just to point a little something out, although work and energy are extremely similar, one major difference is that energy is not a vector quantity like work. Because work involves vector quantities like force and displacement, you have to pay careful attention to direction when calculating it. But energy is a scalar quantity. The direction does not affect the outcome. This is just a little something you should know. And with this out of the way, we'll take a quick look at another important type of energy, which is friction.
Friction is the force that tries to stop materials from sliding or rubbing across each other. So if you rub your hands together, friction occurs. It's the same thing between your shoes at the ground when you walk. Here are some useful properties you should know about friction. Friction is always in the opposite direction of motion. So if a block moving to the right is sliding against the floor, friction will be in the left. Another property is friction is not an active force, unlike kinetic or potential energy. Something can't be converted into friction. Instead, that something is eaten up by friction. And the last property is that friction arises as a reaction to some applied force. So it can never be longer than that applied force. Alright, with that out of the way, we can finally move on to our last topic of the day, which is power.
The rate at which something can be done is called power. The SI unit for power is watt. Its abbreviation is just a W, a capital W. So, a power of 1 watt means that work is being done, or energy is transformed at the rate of 1 joule per second. The equations for power are pretty straightforward. Power equals work done over time taken, or energy transformed over time taken. A quick example is that if an engine does 1000 joules of work in 2 seconds, its power is just 500 watts or 500 joules per second.
Let's say we have a car traveling at a constant speed of 30 meters per second to the right. If the total frictional force of the car is 700 newtons, what useful power output does the engine driver to the driving wheels? Alright, well, since the speed isn't changing, the car most first has to give out a force of 700 newtons to balance the friction. So in 1 second, this 700 newtons will move the car 30 meters. We can figure out the work done by using the equation earlier. Work done equals force multiplied by displacement. When we plug everything in, we get 700 newtons multiplied by 30 meters equals work done, which is just 21,000 joules. Since the engine has done 21,000 joules of work per second, its power is 21,000 watts.
This same equation could have been solved using the equation useful power output equals force multiplied by speed. If we use this equation, we could have simply plugged in the 700 newtons needed to balance out the friction, and multiplied times speed of the car, which is 30 meters per second. In the end, we still get the same result. Isn't it awesome how you can get the same answer with such different ways?
Anyways, this is all we have for today in our tutorial. We hope you guys found this video useful and actually learned something that will help you out in the future. And most importantly, thanks for watching. Our group members are me, Derek Roberts, Taye Mortley, McLennon, Daniel Cotter, Cullen Alexander, and Shem Louisy. Thank you.